now started. Okay. So what I'm going to do today is to give you a preview of what you'll be doing at the lab today. There is the leftover stuff, from from last Thursday, that's due today, anytime today. So it's not just at the lab, but you do get this new assignment that is due on Thursday. So today is Tuesday, it's due on Thursday, which means you have basically a little more than 2 days to work on this. Now this one is slightly more complicated, so that's why I'm using the lecture time to describe it, and also to kind of show you how to use the tools, because some of you may be new to the tools. So first of all, there is a link to quote-unquote this file. So what you do is you open it up, and it will bring you to a Google document. So in the Google document, it will first ask you about your student ID, and because this document belongs to me, you cannot actually edit it. So what you need to do is to make a copy of this to your own personal Google Drive, then you can edit that one, okay? So to do that, you go to File, and then you go to, I haven't signed in yet, so I have to go through the same process too. So I'm going to sign into, okay, well, I think it automatically signed me into, okay, so this is good because I just signed into an account that is not my Los Rios account, so I can show you exactly what you need to do, because otherwise it's pretty hard to show. So you go under File, and there are several options that seem to be the same. Make a copy is what you need. Do not download, okay? This probably will not work in Excel nor LibreOffice, so go ahead and just make a copy to your own drive. So you basically want to make it to your own drive, change the name first, but then you go to Folder, and you probably want to go all the way to the top. Okay, so you want to go back, and then go to My Drive, because the moment you get to My Drive, it is actually your Google Drive. So once you get to your Google Drive, just click any subfolder if you want to put it into a subfolder, and then click Select. And also kind of make sure that you change the name so it makes sense to you, okay? So I'm just going to keep the name of copy of negative exponent problem generator. Click OK. And not only does it make a copy, it opens the document directly in your Google Drive. So how can you tell whether it is in your Google Drive or the original? Well, if it says copy of, or whatever name you choose to use, it is your copy. If it doesn't have copy of, and it's just negative exponent problem generator, it's most likely my copy. And one way to tell right away is whether you can change it or not. So I can show you side by side. This is the one that is on my Los Rios account. This is the one that is linked. You can see how some of the options are grayed out because you cannot change it. And this is the copy that I have just made. And you can see, I can now change all that stuff. So the first thing you need to do is to change your student ID. And then press the Enter key, and you will see the number to test, which is highlighted in green, is changed. So that basically is your number to test for your homework assignment. So everybody's going to get a slightly different value to test. Is that okay? So now the question is, okay, but what about the rest of the homework assignment? The rest of the homework assignment is also described here. So I have just done the first part, copy the file to your own Google Drive. We edit it, we use our own student ID, and then the cell displayed or string displayed in the green cell is what you need to use as input to your program. So this, is also a hyperlink. So what you want to do is, once again, if you want to make sure you don't lose your original page, just right-click on it and then click Download. Okay, and it's a zip file, which means you should be able to open it in on the Mac OS X, in Windows, or in Linux. Doesn't really matter what operating system you're using. And you want to remember where you put it. Okay, I'm just putting it into my home folder on this machine. Click Save, and it's downloaded. It's a pretty small file, so it shouldn't take long at all to download it. So once you download it, okay, read further instructions. So this is an archive of the CodeBlocks project that you can start with. Unzip the archive into its own folder. When you unzip it, it does create its own folder. So there's no need to create a folder first. It will create a new folder in whatever folder you unzip it from. A CodeBlocks project is already created. Edit the file, exponent 10 to 2, and implement exponent 10 to exponent 2. Okay, so that's your job. So let me go to the folder and demonstrate what I mean by unzipping it and what files you will get to see. So I'm just doing unzip here. The file name is, okay, what was it again? Double one. So the file name is double1.zip. Do the unzip, and you can see how it's creating double one as a subfolder. And inside the subfolder, there are a few files. So we'll go ahead and go into the subfolder. And inside the subfolder, you have a choice, okay? If you want to use CodeBlocks, you can go ahead and use CodeBlocks. Some of you are familiar with that because that's what we use in cisp310. On the other hand, if you go like, well, I don't really like CodeBlocks, I would much rather just use a C compiler, you can do that as well. The source files are all here. The .c file is the C source code. The .h file are the header files. So those are the files that you need in order to compile this with just GCC if you want to use just GCC. Oh, okay. So how many people know how to use CodeBlocks, which is an IDE of C and C++? Okay, so most people do. If you do not know how to use CodeBlocks, I can show you how to use CodeBlocks. I think that might be easier than using GCC and Make because that's more of a hassle. You can do it, it's just more of a hassle. All of the lab machines have CodeBlocks already installed. So once you download, unzip this file, you can use CodeBlocks to open the CBP file. Okay, this is the project file. CBP stands for CodeBlocks Project. So if you know how to use CodeBlocks already, just double click on that file. If you don't, I can show you. And you can also install CodeBlocks on any platform for free. It's an open source program. So I'm going to show you that next. So right here. Okay, so the rest is actual descriptions of the coding, which I will talk about in just a little bit. But before I go there, let me just show you how to find CodeBlocks. So just search for CodeBlocks, and the official name is code::blocks, but it's a free software. Go to downloads and locate, okay, where is it? Download the binary release. And now you have a variety of platforms. So if you're using Windows, choose one of these. But be careful which one you choose because only one is suitable. And I would choose this one here. CodeBlocks with -setup because you will need main W in order to get GDB and the whole suite. Okay, so go for the fourth item from the top. That's the one that you need. And for those of you who are using Linux, it has versions for Debian, for Fedora, and I'm not sure what this one is for. And then there's also one for Mac OS X. So regardless of which platform you're using, there's one version for you. The lab machines already have CodeBlocks already installed. Obviously, that one is for Windows. But all you have to do when you're done is to zip up your file, send it to yourself through Gmail, and then when you get home, get it from your Gmail, and then unzip it. You can continue to work on it. Yes?
Can you use Visual Studios?
You can try. It may work. I do not know. I don't have Windows. Yeah. So if you want to use any other tools, you are more than welcome to. It's just that when you turn it in, it has to be in a form that I can see, that I can compile. You can just give me the source files. I can deal with that. Okay? But it cannot be in C# because I don't have a C# compiler.
So you want the CBP file?
I want a .c file. So it's plain C. No C, plus plus. Yeah. All right. So are there any questions about how to get CodeBlocks? No questions? This is all good? All right. So if there are no questions about CodeBlocks, I'll show you how to open it in CodeBlocks. So you can go to CodeBlocks. Okay. In my case, it's under development, under CodeBlocks. It's an IDE which stands for Integrated Development Environment. Okay. And I have an older version. It's only 16.01, but it should still work. So go to File, go to Open, and then it's in my home folder under /1, which is down here. And remember, the CBP file is the one that you need to open because it's the project file. So you click Open, and here we have the full project. All right. So are there any questions about how to open the project file once you have CodeBlocks installed? Is that part okay? All right. So once we have that part done, what I will do next is I'll just give you a tour of the program itself, not CodeBlocks, but the actual source code. This is a little bit small, so I'm going to open it in a larger, or a window that has a larger font. And the first one I want to show is main. So this is main. This part should not be surprising anymore. Main takes on argc, the argument count, and argv, which are the argument values. We talked about that on Tuesday. Okay. It has done all the parsing for you. Okay, so no need to kind of deal with the parsing. And so parse is already done. This part is already done. It's very similar to the one that we talked about on Tuesday, but it's not exactly the same. It will get the same thing done. Okay, so no worries about that part. What you need to do is to work with exp10 to exp2. That's a subroutine that you have to implement. And the criteria for the answer that you are going to be graded on will be discussed a little bit later. So in this case, I do have a type defined. If you go back to the beginning, there's a header file called parse.h, and also another header file called exp10 to 2.h. So let's take a look at those files. Parse.h, oops, okay, parse.h. So parse.h defines a parse state, okay, which then relies on a parse number structure. So to understand what a number structure is, go to number.h, and this is it. It's very similar to the one that we talked about the other day. It has got a mantissa. It has got an exp10 or the exponent in base 10, but it also has a exp2, which is the exponent in base 2. So there's a very minor difference between this structure and the one that we talked about on Tuesday. One is mantissa is no longer man10. It's just a mixed mantissa. Okay, so it's actually the mantissa for both base 2 and base 10. We'll talk about that next. There's an exp10, which serves exactly the same purpose as the member exp10 from Tuesday. And there's a new member called exp2, which is something that we'll work with today, that I'll explain today. So are we good so far with the navigation of files, what header file you might need to take a look at, and so on and so forth? Yeah? Okay. Okay, so the next thing we need to do is to say, but how do I test my program? Because that's going to be kind of important. So to test your program, what you need to do is to look at your own number. Okay, so my number is 8.424e minus 19. Okay, so I'm going to take note of that, or even just copy it, Control C. I go back to CodeBlocks. Okay. And under CodeBlocks, now this part is kind of important because you have to go to Project. Under Project, you want to go to Set Programs Arguments. And then under that, you want to go to the Debug portion, and then click on Program Arguments, and then type in -n, and then whatever the number is. So hopefully Control V would paste it, and it does. So this is how you test your program. unless you want to run the executable on the command line. But if you run the program on the command line, you won't be able to use the debugger. So I would strongly recommend to do it this way so that you do not need to run it on the command line. And then you can use the GUI for debugging the program. So do we have any questions about this step? Everything is being recorded, so the whole process is actually recorded. Okay, so assuming you have this one done, okay, you click OK, like that. Now, we can also look at the source files just by using the browser. So I can now go to exp1022.c, which consists of an empty function. And the empty function is the one that you have to implement. In very faint, right now because it's in comments, it says in this function, convert the number pointed to from a base 10 mantissa and exponent to a base 2 mantissa and exponent. Divide into two main cases, when exp10 is greater than 0 and when exp10 is less than 0. This homework assignment is only concerned about when exp10 is less than 0. So do not worry about what if exp10 is greater than 0, only be concerned about what if it is less than 0. Are we okay so far with that? So in the lecture later, okay, in the next hour or so, I will talk about the logic to do all that. Is that okay? So you'll be writing some code here, and obviously there's nothing here right now, but I'm going to put a breakpoint here. In other words, I just want to run the program and see what kind of structure number looks like when I get here with the -n and then the number that I'm given with. Is that okay? So how do we run this program? It sounds really simple, but there's a little bit trick to it. You go to debug, okay? So do not click the green play button, because the green play button is going to run the production or the release version. It's going to bypass the debugger. So it's not going to hit the breakpoint. It's not going to be very helpful. So what you want to do is to go to debug and then click run under debug. Or start, sorry. So you want to go to debug and then start debug. And if everything works, it will give you a command prompt, and eventually it will stop at the breakpoint. Once you stop at the breakpoint, see how you have an interactive command line here. This is the command that you can use to enter GDB commands directly. In other words, even though it is a GUI, you can use the GUI way of looking at things, but you can also use the command line to directly enter GDB commands. I am much more used to GDB commands, so I'm just going to say print whatever pn points to, and it shows me what pn is pointing to. It says the mantissa is 8,424, which is correct because the mantissa of the given number is 8.424. So according to the logic that we already discussed on Tuesday, it is perfectly okay for the mantissa, which is an unsigned 64-bit number, to be 8,424. The exponent, let me check on the original exponent in the spreadsheet. The original exponent is -19, and right now it is -22. But that's correct also, because when 8.424 becomes 8,000 something, I have to divide 1,000 somewhere to counter that. So instead of dividing by 1,000, I basically just decrease the exponent of base 10 by 3. So now, if you look at the mantissa times 10 to the power of the exponent of 10, it still represents exactly the same value. It just looks a little different. Are we good so far? So your objective is to have this number representing exactly the same value, but I want exp10 to go all the way down to 0. And exp2 has to be a particular value, and then the mantissa also has to be within a certain range of values. That part is described in the homework, and I'll talk about that. But as far as mechanically how to use the tools, are we clear about how to use the tool? That's good? All right. What if you are a command line die-hard programmer, and you go like, I don't want no stinking IDE? What do you do? Well, obviously, we can do it that way too. Okay, so we'll save the changes. It says debugging is going to be closed. Okay, fine. So you go to the command line and you look up all the .c files. Okay, I don't want to waste time at this point to talk about make files and stuff like that. So there's no need to do that. So what we'll just do is just to brute force it. Okay, we'll just say your gcc-g to include debug information. I would personally enter warn all, okay, just so that the compiler can catch potential problems and warn you about those potential problems, but it's optional. -O to specify the name of the output file. I'll just call it main to be consistent. And then you just give it all the .c files. So you've got main.c, you got parse.c, you got exp10 to 2.c, and then just press the enter key. That's it. On the command line, this is how you compile the program with debug information. To debug the program, you use gdb and the name of the executable, which is main. And now you can say list main. The main is the name of the main subroutine. So you can do that, or you can say list exp10 to 2. Okay, it has to find a file first. So I'm going to say list exp10 to 2.c :1. So that goes from line 1. And I'm going to put a breakpoint on line 11 of this file. Run the program again. But this time when you run, you have to remember to enter -n 8.424e -19 yourself. And then press the enter key. I get to the breakpoint. I can now say print whatever the parameter is. The parameter is called pn. Pn is just a pointer, so it doesn't really make a whole lot of sense to print the pointer itself. You want to print whatever the pointer is pointing to, which is the structure, and I get back exactly the same thing. So you can do it through CodeBlocks if you want to. If you know, or if you have a Power account already and you say, I want to do it on the Power server, you can do it that way as well. Okay. Are there any questions?
For print PN, you have it formatted there. Is that part of the program?
Which one?
The second to the last line.
Print asterisk PN?
The line, the line under that.
That's automatic.
That's automatic for
Yeah.
me?
So GDB understands, from the debug information in the executable, it knows what the type of PN is, and it knows what the structure looks like. What the structure pointed to by PN, it also understands what the structure looks like, and that's why it's able to give you a full display of its members, which is handy because we do want to know what the members look like. So are there any questions about both methods, okay, through the CodeBlocks IDE or through the command line if you do not want to use the IDE? Is that good so far? Okay, all right. So the rest of today's class is about the actual concepts that you need to understand in order to get the rest done. So the criteria for grading this one is when your program is done, I want to preserve the value. In other words, V is always going to be the same. V is the mantissa times 2 to the power of exp2 times 10 to the power of exp10. I want that value to be as close as possible to the original one. Okay? So when you nudge exp10 to try to get exp10 up to 0, you can change mantissa, you can change exp2 to compensate for what you are doing to exp10. So we'll talk about strategies of how to do that today. Is that good? Okay. So what would be considered a correct answer? So the correct answer is your mantissa should end up as a value that has bit 63 set, which means bit 63, the most significant bit, should be a 1. Remember, your mantissa is an unsigned 64-bit number. Okay? exp10 should be 0, and the exp2 can be any integer that is signed, as long as we are still representing the same value as before. Okay? And then the represented value V should be preserved as much as possible. In other words, I'm going to write my own code that will do the conversion, and it will preserve the value as close as possible. And then I'll look at your answer and compare that to my answer. If yours come close but not quite exactly the same, you will get points nudged, because of not meeting this requirement. And if your Mantissa does not meet this requirement, that will also be points nudged. Okay. In the following editor area, indicate the following when your code completes. Tell me what the Mantissa looks like. Just copy and paste, either from CodeBlocks or from the command line GDB line, and also what EXP looks like. Yes.
I'm having trouble understanding what you mean when you say preserve V as much as possible.
Preserve V.
Yeah, I just.
Well, okay. So in the conversion process, the value is not going to be exactly the same. In other words, things that we can represent in base 10, we cannot represent some of those values exactly the same way in base 2.
Yeah.
So if you cannot represent it as exactly in base 2, so even the best answer is not going to be exact. But I want your answer to be as close as possible to the original value expressed as a base 10 scientific notation.
So some kind of rounding we do that keeps it as close.
Yep, and we'll talk about that in today's lecture.
Okay.
All right. So any other questions about the description of the homework assignment? Not so much, what to do to get it like this, but just, the criteria that I'm going to use for grading, and also mechanically, what tool do you need to use, and how to install those tools. Are there any questions about that? No questions? All right. Now, I do want to point out one thing that may or may not be useful for this homework assignment. But for those of you who want to kind of play with Google Cloud Platform, which is a very interesting platform for apps and stuff like that, not for assembly language, but I think it might have a GCC environment that's available that's easy to use. So, you can just look up Google Cloud Shell. And Google Cloud Shell is basically a shell environment that you can start up from a browser. And it has some tools already installed. I'm not really sure about GDB and GCC, so those may or may not be installed. But if those are already installed, you can try it out, and you have to pay for it, okay? But they are going to give you a $300 credit, so you can try it for free. And it doesn't cost actual money to use a Google Shell. It comes with 5 gigabytes of persistence storage. So every time you start it up, whatever you have saved in the previous session will still be there. So it's kind of a cool, really free way to give it a try. And when the free trial period is up, you just cancel your account and go like, nope, don't want it anymore. See ya. Okay. So it might be an interesting thing to look into, because then you don't have to install anything. But be warned, it can only deal with command line tools. So you will have to do a GCC to compile, GDB to debug. It does have VI and Nano installed as editors. So one thing that you can look into if you're so inclined, if you're also taking another class using the Power Server, you can use the Power Server. That's pretty easy. All right. So now that I get your attention, we can now start to look into, so how are we going to get this job done? The homework assignment says we have to do the conversions. So how do we get the conversion done? So that gets us back to the notes. Let me go back to the modules. I'm not going to lose the homework assignment description just in case we need to get back to it. And everything that you need to know is in floating point number representation. And we can scroll down to, well, the parsing part is done already. So this part is already discussed on Tuesday. So we can scroll down to conversion from base 10 scientific notation to a double. getting rid of the decimal point, we have done it already. Getting rid of the exponent of 10. So this is the portion where things get a little bit interesting. So even the notation is a little bit different. The scientific notation in base 10 or the floating point representation in base 2, they're pretty much the same thing. Okay, so when I say the scientific notation, that's basically just how you enter numbers on a calculator and how you enter numbers in C and C++, your source code. When we talk about the double representation, it's basically how we use individual bits in a double precision floating point number, but they are really about the same thing, because the bottom line is there's a mantissa, there's an exponent of in base 2, and there's an exponent in base 10. But tech, the scientific notation in base 10 doesn't really have an E2 component. Well, think of E2 as 0 then. Okay? So there's always an E2, there's always an E10. So the idea is we don't want E10 to be non-zero. We want E10 to be exactly 0. But we don't want the value to be preserved, so V should still be the same. So the idea is, sum up in this sentence, you gradually make E10, the exponent in base 10, to 0 by adjusting not just one, but both of M mantissa and the exponent in base 2. You will need both of those to help you. Is that okay? Okay, all right. So the first thing we encountered, this is one of the problems that we saw on Tuesday, is rounding. So, okay, so let me switch to the tablet to explain this. Okay. All right, so let's talk about integer division first, okay? So this is integer division, okay, which is the default way of dividing in C and C++, and we're only dealing with unsigned integers. So in an unsigned integer, what happens when I divide, let's say 31 by, I don't know, let's find 4, okay. So 31 divided by 4 as unsigned integers, this is an unsigned division. What result am I getting back? 7. Okay, because 7 is the largest integer that is still less than or equal to the actual value of 31 divided by 4. Okay, what about 30? What about 30 divided by 4? What is that going to give me? Also 7. Okay. What about 29 divided by 4? That's also 7. And 28 divided by 4 is also 7. So these 4 numerators will give me exactly the same quotient when I am only looking at the integer part of the result of the division. Is that making any sense? Okay. But that's not right, okay? Because 31 divided by 4 is 7, but it really has a remainder of 3, okay? 30 divided by 4 is a remainder of 2, and so on. So every single time when I say 31 divided by 4 is 7, it has an error, right? So what is the error here? So I'm going to use this column for the error. So in the first case, the error is, it's off by 0.75, 3/4, right? And this one is off by 0.5, this one's off by 0.25, and this one is exact, it has no error. Is that okay? Do you see all of these errors are in the same direction? They're all erring in the same direction. So that means, if you only rely on integer division in the math that we are going to have to use, every single time you have an error, it's going to err in one direction. The result is smaller than what it should be. And it's going to be cumulative, right? Because the result of one division eventually is going to be used in the second division, and then the result of the second division is eventually used in the third division, and so on. So if every single time you divide, there's an error that is in one single direction, they're all going to be cumulative. So in the end, after the conversion, the value that you end up with is going to be significantly smaller than what it should be. Is that making any sense? It's kind of like, having your alignment off, when you're driving a car, okay? So if you let go of the steering wheel, it's going to skew to one side, and if you don't correct it, it's going to like veer way off, over a long distance. Is that okay? So what we're going to do next is to say, well, what if we do the rounding, okay? So I'm going to say, rounded result over here. So the rounded result with 31 divided by 4, which is 7.75, what is the rounded result of 7.75? 8, okay? So the error, or the rounded error, is what? Negative 0.25. It's in the opposite direction. What about the second one? The second one, if I round it, it's also going to be 8. Because the actual result is 7.5. When you round 7.5, it rounds up to 8. So the error in this case is negative 0.5. What about this one? Well, this one is still going to be 7, because 7.25, which is the exact result of 29 divided by 4, the rounded result is just 7. So the error is still going to be a 0.25. All right. And the last one is going to have an error of 0 still. But you can see when you're doing rounding, sometimes your error is going to be in this direction, and sometimes it's going to be in the other direction. Which means if you do rounding instead of truncation or integer division, then yes, you will still end up with errors. I mean, if we don't have enough bits to represent the result, we don't have enough bits to represent the result. But because the error is going to be, sometimes it's on the positive side, sometimes it's on the negative side, they tend to cancel out each other. So you can kind of look at this one as not an alignment issue with your steering. Instead, it's just a little bit jittery, okay? But it keeps going left, right, left, right, left, left, right, right, left, right, and so on. So in the end, you're still going to go fairly straight, okay? Even though, if you look at the micro, direction, it does change a little bit, but it's not cumulative. It's not always going in one direction. Is that okay? So this is the reason why we have to integrate rounding in all the math that we're going to do when we do the conversion. Is that okay? The rationale of rounding. So once we understand why rounding is important, the next question is, how do we do rounding? Okay, so in general, when you do rounding, okay, round 1.7 is 2, round 1.1 is 1, and so on. Okay, sounds like we need to use a double function, but I do not want you to use the double type at all in your program. Okay, so no use of double arithmetics, no use of double functions whatsoever in your program. How do we do rounding without using doubles? Well, as it turns out, every single time we need rounding, it's applied to the result of a division. Okay. In other words, every single time we want to do a round, it has to do with some kind of division. So in the notes, it says n divided by d. Okay. And n, we know n is an unsigned 64-bit integer, and d is a much smaller integer value. But we know they're both integers. Is that okay? All right. So what we're going to do is to say, it really is the same thing as this plus 0.5 and then take the floor function of it. Because in general, what round is just like that, okay? So in general, round of x is the floor of x plus 0.5. And if you're not convinced, you can try it out. Let's try out 1.7. What is 1.7 plus 0.5? 2.2. What is the floor of 2.2? 2. Oh, okay. So we got the correct result. What about 1.1? What do we get after we add 0.5 to 1.1? 1.6. What is the floor of 1.6? 1. Okay. Let's try a boundary case. Okay. That one number that that moves on to the next number, which is 1.5. What do you get? What is round 1.5? 2. What is 1.5 plus 0.5? 2. What is the floor of 2? 2. Oh, okay. So if we want to do rounding, but we do not have the rounding function, but instead we have the floor and just addition of a real number, we can do it this way. But that means you still have to represent 0.5, which is something I don't want to have to deal with. I don't want to deal with any type of real numbers. I want to deal with only integer numbers. So then we can say this is n plus 0.5 times d, the whole thing divided by d. I hope your algebra is at least up to this point. Yes? Okay, very good. And okay, so at this point we go like, we are still not getting rid of the 0.5. Okay, well, if you want to get rid of 0.5, we can do it like this. How about d divided by 2? And then the whole thing divided by d. Okay, that gets rid of the 0.5. But now we have division again. Well, it depends on d then. Because if d is an even number, d divided by 2 is going to be a whole number anyway. So we don't need the floating point representation. We don't need real numbers to perform this division, and we get something exact. Is that making any sense? So as it turns out, in base conversion, the divisor is the base, okay, which in base 10 is 10, in base 2 is 2. Is 10 an even number? Is 2 an even number? So as it turns out, this portion always ends up as a whole number. Well, if it's a whole number, can I use integer math to add an integer to another integer and get the exact result? Yes. Can I divide it by another integer? Yeah, but you're not going to get the exact result because integer division is automatically applying the floor. Great. We're doing two things at once. So the division and the floor is combined to what we just call integer division. So that's why this form of rounding is so useful to us, because we can get away with not really needing real numbers in the entire calculation. So what is the whole point of using this instead of using real numbers? What is so bad about using real numbers in terms of addition, subtraction, multiplication, and so on? Well, as it turns out, real numbers takes a lot of juice to process. Okay, I'm not just talking about the conversion, which we are talking about right now. I'm talking about just adding two floating point numbers. It takes a significant amount of energy to compute it, which you never see because your i5 processor, even an i3 processor, has a floating point coprocessor that can get all of that done in hardware really, really fast. So why are we concerned about that? What do you think?
They're like embedded systems that are really puny processor power.
And why do we choose puny processors when we have cool i7, i9 processors?
Power consumption.
Power consumption. And with what application is power consumption such a big deal?
Everything that goes anywhere.
What about my Fitbit? What do you think is going to happen when they try to put an i9 processor with how many cores again? 16, 8, something like that? Yeah, so what if I put a i9 processor on my Fitbit because I need all that processing power? So I will need a heat sink first, right? The heat sink is going to be about the size of my palm, okay? And what about the power consumption of the i9 processor? you need to have, well, I want to recharge my Fitbit every 5 days because that's what I'm doing right now. So what kind of battery pack do I need to carry with me with a Fitbit that's powered by an i9 processor, and I only want to recharge every 5 days? Probably something I don't want to carry with me, right? Okay, so if that is not going to work out, what do you think is the processor inside the Fitbit? I really don't know, but I'm just going to let you guys guess. It's probably going to be an 8 or 16-bit processor that's only capable of integer arithmetics. So it can only add, subtract, compare integer values, maybe multiplication and division in integers, but not floating point numbers. Okay? Well, there you go. Well, if the processor does not natively support floating point number calculations, then every single time you have floating point number calculations, it has to be done by a library of subroutines. And it's going to take a significant amount of juice, which means even though it will still be the same form factor as it is now, but if I do floating point number calculations all the time, my battery is going to die a lot faster than the same software, but only relying on integer arithmetics. So that is why there's a big push in my class, especially for this class, to only utilize inexpensive operations, which basically translates to integer arithmetics and not floating point number arithmetics. Is that okay? Yep.
Can you explain again why D cannot be odd number?
Say that one more time.
Can you explain again why D cannot be odd number?
D cannot be an odd number because every time we do a division, we're dividing by 10 so that we can change exp10, or we may be dividing by 2 so that we have enough room to multiply by 10. So D in our calculation, every time we need a rounding, it's always to the result of a division, and every single time we have a division like that, it's always divided by an even number. And if it's divided by even number, D is even. So D divided by 2 is going to be an exact value, which is a whole number, which comes in very handy to us. So now we can go back to the notes here. All right, so 5.2.1 is basically what we need to focus on to get the homework done. So exponent of 10 is less than 0. So what are we going to do? Well, we want E10 or exp10 to go to 0, which means we want to increment it until it gets to 0. Is that making any sense? All right. Increment. But how can we increment exp10? Incrementing exp10 is if you don't do anything else and you're just adding 1 to exp10, you are multiplying the entire value by 10, which is not what we want to do, right? So in order to increment exp10 by 1, what do I need to do to the mantissa? Divide the mantissa by 10. So if I divide the mantissa by 10, I can bump up exp10 by 1. So if I do it enough times, exp10 will eventually get to 0. Is that making any sense? So that's the general strategy. But if that is the general strategy, then we have a problem, because division by 10 can potentially have a lot of error. So I want you to look at this one. What is 18 divided by 10? Integer math. Okay, so we're only taking the floor of that. 1. Okay, 1 is correct. And what is, let's say we multiply 18 by 4. So 18 times 4 is 72. 72 divided by 10 is, and take the floor of that, is 7. Okay, very good. What about the error in this case in terms of percentage? I just need a rough estimate. So it's 0.8, right? The error itself is 0.8. It's 0.8 out of 1.8, which is what the value is supposed to be. So 0.8 out of 1.8 is what? About 45%-ish, okay? So I'll just call it 45%. So we have an error percentage of about 45%, which is pretty bad. What about this one? What about when we divide 10 by 72? The answer is supposed to be 7.2, but I'm getting 7, which means the error is 0.2, and it's 0.2 out of 7, 7.2. So if you divide 0.2 by 7.2, what do you get? Just approximately. It's the same thing as 1 divided by 36, so I'm just going to call that 3%. Okay? Oh, it's quite a bit better. So this means as long as my divisor is constant, which is 10, okay, the larger I make the dividend, which is also known as the numerator in the fraction, my error will drop. Is that making any sense? So if I try to make my numerator as close as it possibly can be to 64-bit wide, don't you think that would drop my error rate to like almost negligible? Because 64-bit, a 64-bit number is a huge number in base 10. It's going to take 19 digits in base 10 to represent the largest value in 64-bit. So we are talking about 19 digits, which means the worst percentage in terms of error in a division like that is going to be point followed by 17 zeros and then some non-zero values. That sounds pretty good, okay? Even though there's still an error, it's acceptable. Is that making any sense? So that's why we want to increase the dividend as much as possible until it cannot get any bigger. Then we do the division. So that's basically what this line is about. This line here. As long as m is less than or equal to the largest numerator value, minus 5 divided by 2, we perform the following. And by the way, this should be minus 6 divided by 2, not minus 5 divided by 2. Yeah, I can go back and change the notes. 0296. I'll go back and change it. But the point is, we want to get m bigger and bigger and bigger until it cannot get any bigger because it filled up all 64 bits already. Okay? So, but every time you make the mantissa twice as large, how do you make up for that change so that it would still be representing the same value? Remember, m times 2 to the power of e2 times 10 to the power of e10 should never change. That represented value should never change. If I double m, what should I do to compensate for that doubling? Decrease e2 by 1. Okay, so that means every time I double mantissa, I have to decrease the exponent in base 2 by 1. So I keep doing this until I cannot do it any further. And not to be able to do it further is to limit it by this condition. So as long as m is less than, well, actually I have two ways to fix this. As long as m is less than, so just cross out or equal to, or I can say m is less than or equal to blah, 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 and then it's minus 6 instead of minus 5. So either way we'll fix that problem. Okay? Okay, so what do you do about this statement? When I use the words or the phrase as long as, what type of control structure does it translate to in C or C++? A while or for, okay? And for those of you who are Lisp programmers, recursion. Because if you don't have loops, recursion is the only way you can do something repetitively. But that's a different topic. So a while loop would do this. So once you get m to be a really huge, gigantic 64-bit number, then what do? Well, it's time to do the division. Okay? So you perform the division like this. You add 5 to m, and then the whole thing divided by 10. But Tech, you never talked about the floor function in C and C++. How do we do the floor? Well, I think I did talk about it today. Remember in integer division, It's dividing and flooring at the same time. So you don't need the explicit floor. It's already done for you. You just put in parentheses mantissa plus 5, the whole thing divided by 10. It's automatically flooring for you. Is that okay? Yes? No? Kinda? Okay. But if I divide the mantissa by 10, I need to make up for that division by 10, which means I can now add 1 to exp10. What do I do after this? I have to go back and check whether exp10 is still less than 0, right? So that means, this code here, this entire chunk of code is inside what? It has to be done over and over again until exp10 is 0. Wait, I just said this has to be done again and again, right? What kind of control structure in C or C++ is going to do it? Another type of loop, right? Well, not another type, but another loop, okay? It can be a while loop or a for loop. So you have a big for loop on the outside that says as long as exp10 is less than 0, right? And then inside that huge loop, you have a smaller loop that says as long as m can be bigger, let's double it, okay? And after that loop, then you go, okay, now that m is as large as you can possibly get, we're going to have the least amount of error in the division. Let's go ahead and do the division and adjust exp10, and that will be the last thing you do in the outer loop. Is that okay? I don't want to give you the pseudocode because that's like, this is already really close to the pseudocode. So, I'm just going to let you guys, figure out, how to structure the code. All right. So, are there any questions about this part here? Okay. Here, I said right here, there's an overall loop on top to perform these two steps. 1, 2, as long as E10 is less than 0. In other words, I even spell out the actual condition you need to use in the outer loop and also the inner loop. You have to interpret and you have to do your own understanding and your own coding to put all of this into place. But that's your homework assignment. There's no point in me doing your homework assignment. But are there any questions? Do we have all the mechanisms that we need to do this? Yes?
Can you explain one more time how the floor function is already built into what we're doing in integer division?
Okay, so if you, in parentheses, okay, so if you say, okay, let's say m is an unsigned 64-bit number, okay? So when you say m plus 5 and then put the whole thing in parentheses, what is the type of that result? It's an unsigned 64-bit number, right? Okay. When you say that whole thing in parentheses and then you do a slash for division and then a 10, what is the result of that division? Yes. So what happens to the fractional part of that division? Isn't that the same thing as floor? That's what I said. That's what I meant. Yep. Okay. So are we good so far with all of this stuff? So what do you say if I give you a kind of really, I'm trying to think of the term to do it, a really tedious, okay, that's it, the really tedious and mundane example of how these values are going to change using my example in GDB. Do you think that might be helpful? I think it might be helpful. So we'll go ahead and do it. And being a command line person, I'm going to do it in here because I'm already here. Okay, so I look at this and go like, is exp10 less than 0? Yep. I mean, you're staring at exp10 equal to -22. Quite obvious it is less than 0. So we have to go into the loop. Okay, we have to get into the outer loop. What is the first thing we have to do in the outer loop? Look at mantissa. Does Mantissa look like something that fills up all 64 bits of an unsigned 64-bit number? No, not even close. Okay, this fills up, just guesstimating 15 bits. Okay, not even close. So what are we going to do? We have to double it. Okay, so we say set. Okay, this is going to be so tedious. Set var pn points to Mantissa. Okay, let me see what is the best way to do this. Multiply equals 2. Okay, there we go. So there we go. We're doubling it. Okay. How many people are familiar with multiply equals 2 as an operator? Okay, there's a small percentage. Okay. This is called a compound assignment operator, where it is combining a multiplication by 2 with a equal or assignment operation. It really means the same thing as Mantissa equals to Mantissa times 2. Okay, but it's a shorthand. And I like shorthand because, otherwise I would be spending a lot of time to type. The next thing I need to do is to set var pn points to exp2. And what do I need to do to exponent 2 again? I'm doubling the Mantissa. How do I compensate for doubling the value? I have to divide it by 2, which means I have to decrease exp2 by 1. Okay, so decrement would do. So minus equal 1, same thing. All right, and then I take a look at it again. Okay, slightly better, but still not using all 64 bits, right? So what we do is we're going to do the same thing here. And what I'll do now is I'm going to try to combine these two on the same line. I'm not sure whether it would take a semicolon and do something else. Oh, it doesn't like that at all. Darn. Okay, that's. Oh, I can do this. Comma. Okay. Yeah. See? That works. Okay, not there yet. Not there yet. As I said, mundane. Okay. Do you see what I'm doing here? You can see how exp2 is decrementing, and you can also see how Mantissa is bumping up. Every single step is doubling the Mantissa, and then the exponent is decreasing by 1. Okay. Oh, how do I know whether Mantissa is meeting that requirement or not? Okay, so let's go ahead and double again. But this time, instead of printing pn, I'm going to test it to see whether it is at the point where I can stop or not. Okay. So I'm going to look at the comparison of Mantissa, and I want to see if it is still less than, remember that number? It's 2 to the power of 64 minus 1, and then the whole thing minus 5. So that would be 2. That would be 2. Okay, so if I'm just going to type it out first. 2 to the power of 64 minus 1, which is the largest unsigned integer value you can represent. But we also want to minus 5 from it because we are adding 5 before the subtraction, before the division by 10. Okay, so when you look at this number and go like, oh, we can combine the 6. Oh, there's also the doubling. So we want to kind of do the division by 2 thing. Okay. So when you look at this, it go like, wow, that's a pretty big number to enter. It's going to have 19 digits. Well, I mean, if you feel like typing in a 19-digit number, go ahead. But I'm not going to do it. So what am I going to do? What is 2 to the power of 64? How can I represent that? What about this? Okay, so I'm going to do it this way first, and then we'll do some simplification. Don't you think that means the same thing? This is the left shift operator. If I left shift once, it is doubling. If I left shift twice, it is quadrupling, and so on. So if I left shift 64 times, it's the same thing as 2 to the power of 64. Have you guys learned about the left shift operator? Okay. So the left shift operator means you're shifting the binary bits with an integer value. You're shifting everything to the left by 1 position. So if your original bit is 0100, it becomes 1000. The 1 got moved to the left by 1 position. Every bit is moved to the left by 1 position. And then the rightmost digit gets a 0. Is that okay? So, but that's doubling. That's doubling in base 2. Okay? So that's why 1 left shift 64 times is really the same thing as 2 to the power of 64. Okay? But we cannot represent 1 left shift 64 times because that actually requires 65 bits to represent it. Okay. So we can apply the division first. 1 left shift 64 times divided by 2 is 1 left shift 63 times. Okay. So we change this to 63. What about 6 divided by 2? That's just 3, right? So now we have this value to compare to. But hold on a second here. This 1, what is the type of 1 as a constant in C? It's an int. An int, how wide is an int? It kind of depends. If you are dealing with a 64-bit architecture, it might be a 64-bit number, but int, I think by default, is only 32-bit wide. So if you have a 32-bit number and you left shift it 63 times, it's going to be 0 because you're stuffing 63 zeros into a 32-bit number, so you're pushing out every single bit out of the 32-bit number. That's not going to work. So we have to cast the 1 into a uint64 underscore t first. That will make this one 64-bit wide. If that one is 64-bit wide, then we can actually right shift it. Excuse me, left shift it 63 times. So that becomes the most significant one on that side. And -3, so that looks like it will work. Okay, so it's still less than. So we perform another doubling. It's still less than. Perform another doubling. So we keep doing this. Okay. 63 minus 3. I think I really should be comparing it to 62. Yeah, it should be 62. Okay. So in the worst case, I have to do this, how many times? 63 times. And we have done it how many times again? 30 times, actually 15 times only. Let's print what is PM pointing to. EXP2 is 28, so we have done it 28 times at this point. And the Mantissa has how many digits? It has got 3, 6, 9, 12, 13 digits. And it's going to look like a 19-digit number when we are done. So we have some ways to go. Double again, check again, double again, check again, double again, check again, double again, check again. Is there any question about why we should do this in the loop? Well, we're getting closer. Oh, darn it. Oh, I missed it. Crap. Okay. So I just missed it. So now the number is no longer what I want because it has overflown a 64-bit number. So we will probably have to do it again from the beginning. Okay, so let's just say that it is. It's okay. Okay, so let's just say that it is at this point, the value that we want. Okay, this is not the value. I can guarantee you it's already past that point. But let's say it is. What are we going to do? We want to divide the mantissa by 10, but we want to take rounding into consideration, which means we have to do something that looks like this. Okay, this equals to in parentheses pn mantissa plus 5, the whole thing divided by 10, right? Because that takes into consideration that we want to perform rounding. And then the next thing we have to do is to go take a look at exp10. Oops. I call it something else probably. Yeah. Nope, it doesn't want to show me what pn has. Uh-oh. Is it pn? Yep, it is pn. Oh, set var pn. I want to print pn. There we go. It is called exp10. Okay. So now we want to do a set var pn points to exp10 to minus equal, plus equal to 1 because we want to bump it up by 1 because we just do a division with a mantissa. So now we're at the end of the outer loop. What do we do to decide whether we should go for another iteration or not? We check exp10, right? So we say print pn points to exp10. Doesn't look like 0 to me. Looks like it's still less than 0. So let's do this whole thing again. But the next time it's not going to be quite as bad because you can see the mantissa is pretty big already. So it will only need a few bumps, to get to the limit before another division. So it's only the first time that it has to go through like 60 something, close to 60 times of doubling to get to that point. But once it gets to that point, because I'm only dividing by 10, right? If you divide a 64-bit number by 10, okay, how many times do you think you have to double it again to fill up all 64 bits again? Okay, let me make it easier. If you divide it by 8, how many times do you think you have to double it again to fill up all 64 bits? 3 times. But 10 is greater than 8. Okay, so let me ask you another question. What if I'm dividing by 16 then? We have to left shift it 4 more times to fill it back up again. So it's going to be between 3 to 4 times. So after the first time that you bump it up all the way to 64-bit wide, all the subsequent left shift operations only need between 3 to 4 times to get it to fill up all 64 bits again. Yes? Say that one more time.
So one left shifted 62 times
Mm-hmm.
is equal to 2 raised to the 63.
One left shift, okay, one left shift 62 times is 2 to the power of 62, which is what I want. Yeah, so initially I was using the wrong condition. Okay, let me show you why I need that. Because the largest numerical value is 2 to the power of 64 minus 1. So it becomes 2 to the power 64 minus 5, minus 1 minus 5, which is minus 6, and then the whole thing divided by 2, which is 2 to the power 63. So you're right. So this has to be 1 left shift 63 times minus 3. You're correct. Yep. So the check that I was using here was not correct. Should have used, this should be 63, not 62. So you're correct. So this is the correct way to check whether we need to double or not. So, okay, so let's say we are going back to the inner loop. So this says we have to go for another iteration. So now we go for the doubling again. Check again, double again, check again, double again, check again, done. Okay, so now we take a look at PN, whoops, Mantissa. And what do you think about the, okay, so we look at this number and go like, well, is this really the largest number we can represent that is still less than or equal to the, it's the largest, I should have put it, this is the most we can double the mantissa before it overflows a 64-bit unsigned integer. How do we know this? What is the other way, instead of using this, what is the other way to tell us that, if we double again, it's going to exceed what we can represent? You can use a calculator. Okay, if you use a calculator, you can easily find out. What about the other ways to do it? Let's print this out as a hexadecimal number and see if we can get some clues out of that. Okay, print /x, so it will be in hexadecimal this time, and it looks like this. Actually, it does look like we can double it again. Yeah, it does look like we can double it again. So this condition, well, let's see. How many digits are we looking at? There should be 16 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we do have 16 digits. The most significant one of the hexadecimal representation is representing the most significant 4 bits. So what does 1 look like as a 4-bit binary number? 0, 0, 0, 1. So the most significant bit is definitely not a 1. So that means the comparison is not correct, because the mantissa we should still be able to double it 3 more times before it gets to the point where it cannot double again. So I'm looking at the condition and go like, why is it? I think I might know. It probably has to do with the priority of operators. It's probably doing the subtraction before the shift. So I'm only shifting it 60 times instead of 63 times. So that is why we have that problem. Okay, so we'll go back to this condition and go like, well, let's be very clear about what we want to do first, okay? And it goes like, well, it's still that. Oh, that's not what I want. That's the opposite of what I want. Duh. Okay, so let's try the other way to arrange the parentheses. Feel much better. Okay, so that means we can still double. And check again, double, check again, double, check again. Now we should be fine. Okay, so we'll take a look at mantissa in base 16 again. And this time is blah, 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 okay? So let's count the digits again. That should be 16 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Very good. The most significant digit in base 16 is a D, okay? D is basically the same as 13 in base 10. So what is the 4-bit representation of 13? It's got an 8, it's got a 4, got a 1. So it's 1, 1, 0, 1, which means the most significant bit of this 64-bit number is in fact a 1. Now, if the most significant bit of a 64-bit number is a 1 already, that means you cannot double it without losing the value. So this is a double check to make sure that my math is actually sane, because well, earlier it looks right, except the priority of the operators was incorrect, because I was assuming that it would do the left shift before the subtraction, but in reality it performed the subtraction before the left shift operation. So that kind of messed it up. Is that okay? We are running out of time. This is actually right on time. It's 10:20 right now. Doesn't get any better. Okay, so what are you going to do about all of this stuff here? How is this helping with your program? I have basically just spelled out all the conditions, all the operations. All you have to know is where to put the open and the closed curly braces. Well, I mean, but there are a lot of degrees of freedom there too. Well, there's a little bit more than that. So you have to read the assignment constraint very carefully, because what you turn in has to be the largest possible number with the mantissa. So that's the tricky part.